Accessing real-world objects in immersive VR is often restricted by rigid setups or the need for tracking markers. To solve this, we developed SelfBlending, a framework that enables the enrollment of uninstrumented physical objects without relying on hardware-based tracking. SelfBlending empowers users to register surrounding physical objects via simple freehand labeling and selectively blend them into the virtual environment. SelfBlending facilitates this integration through a media pipe hand tracking model deployed on the streamed color image. To delineate the 2D boundary of an object, a user points with their index finger. If the position remains unchanged, the system registers a 2D coordinate. After the user inputs the required points, the system automatically generates a rectangular bounding box. Once labeled, the system transitions into a tracking phase to capture diverse visual representations from multiple viewpoints. To achieve this, the system leverages 6 degrees of freedom data from an integrated inertial measurement unit for robust tracking. A sensor fusion approach integrates this data with visual information to estimate the object's position and orientation. These multi-view captures are compiled into a dataset for the target object. Following the dataset collection, the label information is stored in annotation files formatted according to the YOLO standard. The dataset, containing RGB images and YOLO formatted annotations, is then used to fine-tune a YOLO model for recognizing the user-defined objects. To support the real-time interaction between the detection module and the Unity-based VR environment, a two-way communication channel is implemented over the local host. Using this interface, Unity sends object requests to a Python-based module that processes the incoming video feed from the external camera. Processed frames containing bounding box data and confidence scores are returned to Unity. These parameters generate a dynamic, masked pass-through window that circumscribes the detected object. This configuration enables selective interaction with real-world objects while maintaining immersive continuity and situational awareness. To evaluate the conditional pass-through technique as a part of the SelfBlending framework, we compared it against 2 common interaction methods: headset off, where participants physically removed the headset to interact with real-world objects, and default pass-through, where the headset's built-in full-view pass-through feature was used. In the conditional pass-through, SelfBlending was employed to selectively blend only the target item into the virtual environment. The experiment setup, illustrated on the left, involved participants wearing a MetaQuest Pro headset equipped with a front-mounted Z mini camera. While immersed in a continuous VR shooting game designed to maintain sustained focus, participants experienced the 3 experimental conditions in a within-subjects design. This study measured the perceived workload, sense of presence, cross-reality interaction experience, interaction time, and the subjective preference of participants. Results demonstrate that conditional pass-through supported immersive continuity, reduced cognitive disruption, and facilitated efficient interaction via selective, context-relevant blending. By offering a lightweight and flexible solution for personalized cross-reality experiences, this work broadens the design space for fluid interactions between physical and virtual worlds. We're excited to share these findings with the community. If you're interested in the details of our framework or the full results of our study, we warmly invite you to dive into our complete paper.